just have to run a command to check it. Okay. So, I'm going to be talking about memory allocation and trying to convince you that it's actually not that hard or that scary. So, why did I actually start messing around with memory allocation? Well, I'm reinventing wheels. I like reinventing wheels. I started off creating my own programming language. And if you're creating your own language, well, you need to have a library. And if you have the standard library, well, why would you use libc? Why not just reinvent everything? So now I know that OS X has 2 different syscall APIs that you need to use both of to actually get a complete set, and that FreeBSD's pipe system call returns values in the wrong places, and this is why I drink. But that's not what the talk's about. Maybe some other time. So, well, let's see how low we can go as far as line count goes for memory allocation without making it unreadable. So it's not like everything's jammed on one line. It's what I think is clean code. So comparing tcmalloc, which is what Google's perf tools gives you, is sitting at 50,000 lines. jmalloc is at 25,000 lines. ptmalloc, which is the one that ships with glibc, so you're probably using it if you're on Linux, it's actually relatively small. It's around 8,000 lines. And the one that I wrote, gemalloc, basically when I went, hey, this is good enough, is around 212 lines for this C implementation. I initially actually implemented it in my own language, but I rewrote it because I wanted to do fair benchmarks and I wanted to actually compare. So after I talk a little bit about how it's implemented, I'll talk about where exactly it falls apart. Why can I do it in 212 lines where everyone else takes thousands? Well, obviously there are some things it doesn't do or doesn't do very well. And how would you go about fixing it? Okay, so slab allocation. That's the name of the core algorithm I'm using. It was introduced by Jeff Bonwick in his paper on slab allocation. I don't actually remember the title. I probably should have put it down here. But so he initially introduced it in 1994, used it in the Solaris kernel, extended it in around 2000 with some other things. And it's the core of many modern allocators. 2 of the ones that I mentioned, jmalloc and tcmalloc, both use it as their general core algorithm, at least for some size classes. And I use it as well. The assumptions I make when in this allocator are that the OS gives us memory map, which basically says, hey, I want a chunk of memory. I want it to be this big. Give me this chunk of memory. So I have a big chunk of memory. You might ask, well, if the OS can give you memory, why do you need an allocator? Why not just call that? It's slow. That's all there is to it. You have to jump into the kernel. The kernel has to look up the memory. It has to fiddle with the page table entries. You have to flush the TLB, the translation look-aside buffer. Basically, there's a lot of hardware stuff that hardware caches that go away whenever you call it mmap, so you don't want to call it very often. The other assumption is that large allocations are going to be rare. So if you allocate a gigabyte of RAM, you'll probably hold on to it for a while. You're not going to be allocating it every few microseconds. So now that I've described the general idea, let's go into how it works. So the allocation data structures, you have a list of buckets. So basically a bucket is a size class. If you're allocating 64 bytes, you're always allocating from the same bucket. The buckets contain slabs. Slabs are chunks of memory which contain a linked list of, well, chunks. And the chunks are what you actually hand out when you allocate them. So, well, I mean, I've got a diagram of it. A beautiful, beautiful ASCII art. So, if you allocate a 16-byte value, you look it up in the buckets, and the bucket points to a slab. The slab has a next pointer, so if you have multiple chunks there, or multiple slabs, you can just get to the next one. But there will always be something free in the first slab, so you can always just pull off of that one which makes it really cheap. And you've got the head of the free list in the slab. So when you allocate, you just grab the first value here and return it. So let's just say you allocate a value, and how does this data structure change? Well, this value is now scribbled over by users because you've just handed it out, and they've probably written values into it. And your free head points to the next guy. So that's basically what you're doing. You're popping. You have a linked list of slabs, and the slab contains a linked list of chunks. And you just pop a value off the slab and return it. And that's all. That's the entire allocator. There's nothing too complicated here. The data structures are something that you cover in the first probably 10 minutes of, okay, maybe not 10 minutes, but within the first few hours of your introductory data structures class. And the code itself, well, here it is. Here are a bunch of constants for describing it. So in my allocator, I actually fall back to mmap for large allocations, and 32 kilobytes is my definition of a large allocation. It's arbitrary, I can pick anything, but 32K sounded like a good number. Slabs, I decided to make them 8 megabytes. Again, an arbitrary choice. Make it too big and now you have to initialize a giant list link of chunks every time you get a new slab. Make it too small, and you're allocating slabs really frequently. Alignment, that's actually part of the ABI spec. So every value that malloc returns on an x86-64 machine has to be aligned to 16 bytes. And I have a little bit of hysteresis so that if I free the last element in the slab, I don't immediately return it to the OS. And the cache for that is 4 slabs. Okay, so the data structures themselves, you have a bucket, you have a slab. Each bucket has a lock, so you can have multiple threads. I've got 3 minutes. And then you have the chunks. So I have so I initialize a fixed set of buckets. Here, there are a few tricks. I'll be happy to dig into them more deeply. And I've just scrolled through the entire chunk of code. I don't think I have time to describe it in detail, so feel free to talk to me afterwards. So the next question is, how did we do? Well, my allocator, for 30 million allocations with 1 thread, it takes 0.59 seconds, which comes out to 19 nanoseconds per allocation. So how does that compare to the other highly optimized implementations? How much better do they do? Well, ptmalloc takes 0.82 seconds, and jmalloc takes 1.01 seconds. Holy shit, I beat them. That's not expected. Well, it turns out that that's partly because it's just really simple. There's a lot of complexity that they put in to improve performance with multi-threaded code. So how do we compare there? Well, with 30 million allocations, 16 threads, ptmalloc takes 24 seconds, jmalloc takes 23 seconds, and gemalloc takes 1 minute 22 seconds. So I'm around 3 to 4 times slower. That's actually also kind of holy shit to me, because I was expecting it to be around 16 to 20 times slower. 3 times, 4 times, that's actually really damn good. And for giant allocations, well, jmalloc blows everyone else out of the water here, which is why I believe Firefox uses it, FreeBSD uses it. It's pretty popular. jmalloc takes 0.13 seconds, gmalloc takes 0.85 seconds. So, okay, I'm actually pretty happy. I can go, good enough. But there's room for improvement. So what can we do? Well, large blocks, I suck at them. I just end them. So what I can do is put the large blocks into, say, a red-black tree or some other fast lookup data structure and basically keep them around and allocate from that instead of jumping into the OS and leaving it into that and doing all the flushes there. magazines, which are basically thread local caches. So right now, if we look back at the code, every bucket has a mutex. If you're allocating from the same bucket over and over, you're going to be hitting that mutex. You're going to be waiting until someone else is done with the mutex, and you're going to be spinning around, and only one person can allocate at once. If you make it per thread, each thread can allocate independently. So there's room for that. And then everything else, I think, is going to be micro-optimizations. Right now, I have a linked list. That means that I can end up playing cache line ping pong. Hey, core over there, I've modified this cache line. Oh, I need to update that. And going back and forth like that. If every core can have its own cache and not modify that way, well, things get faster. Less locking, more atomic operations is another place. A bit of hysteresis in the cache. So right now, if you end up at an exact boundary of 4 slabs, you can end up freeing and returning memory to the OS and bringing it back. So that's basically that. So I guess this usually goes at the start, but if you want to contact me, well, my name's Ori Bernstein. I'm made of meat, and that's my email, and that's my website.